Welcome, ladies and gentlemen. We, Firnas team, introduce face recognition using convolution neural network, CNN. So, let's start with the algorithm we used. This picture shows a cat, but in computer vision it's a 3D matrix, which is called the RGB matrix. First, we flatten this 3D matrix to a column vector. Then we divide element-wise by 255, as we use a 8-bit color, so that we can get a percentage of red, green, and blue in each image. Then we move them to our trained CNN to predict, and as shown, the prediction was 0.73. That means the image is for a cat. And now, moving to how the algorithm works. 1. It gets the RGB of each image. 2. It flattens them to vectors. 3. We put the train input y. 4. We initialize our parameters w and b, where w is a vector of the weight of each pixel and b is a scalar called bias. 5. Apply the sigmoid function to limit our prediction between 0 and 1. 6. Set the number of iterations. 7. And finally, calculate the cost function, trying to get the parameters which represent the minimum cost. Then, update the parameters and save them. We made a simple GUI using Python to facilitate handling the code. Now, we'll show you a tutorial with some experiments.
As you can see, here is our graphical user interface, our GUI. We notice there are several text boxes. The first one is for the training folder path, and the second one is for the text folder path. We put here the path of the test data folders. Also, there are the training input, the test input, the number of iterations, and the learning rate text boxes. We conducted 4 experiments where each one has its own train and test folders. We start with the first experiment, in which we trained the program with 7 true images and 3 false ones. And in the test path, we put 4 true images and 3 false ones. Here, we start to enter the folder's path, and we show the sets to see the results, by which we can enter the training input, number of iterations, and the learning rate. Here, it appears 2 figures. Figure 1 shows a curve with the cost function on the y-axis versus the number of iterations on the x-axis, while figure 2 shows the cost function on the y-axis versus the learning rate on the x-axis. It's clear from the figures that both the number of iterations and the learning rate decrease with the increase of the cost function. We find that the train accuracy is 100% and the test accuracy is 85%, and that's because the program predicted 1. Then we made our second experiment, in which we trained the program with only 1 true image and the other 9 images are false. The test folder contains 2 true images and the other ones are false. We notice here that the second true image contains an expression different than that we trained the program with. We then enter our data, click Show Sets to see them, run and show the results. We have the same result of train 1, that both the number of iterations and the learning rate decrease with the increase of the cost function. We found out that the program made a mistake in predicting a picture
which is obviously the one with the... And now we move on to the third experiment. Here we decided that we will train the program by only one image, the same one used in the second experiment, which is the one with no expression. And then we put in the test path two pictures with no expression and one with a different expression, laughing. Proceeding in the same manner as before, we noticed in the test accuracy that the program predicted the first two photos right and the third one wrong, the one with the laughing, and that the test accuracy was 90%. And finally now, in the last experiment, number 4, we decided to train the program by pictures of laughing expressions, 3 pictures, while in the test we used the same pictures used in experiment 3, 2 normal pictures and one with the laughing expression. We proceed our way, and unexpectedly the test accuracy showed to be 100%, which means that the program predicted all the pictures right. So, we conclude that when we train the machine on a difficult expression like laughing, it could identify it. When not trained on it, it won't identify it.